Okay. I guess now that we're a little more than halfway into the semester, we should finally talk about getting some homework done. So, before we run out of semester. Um, Now, I'm going to spend today talking about um, mainly the MATLAB aspects of getting these problems done, at least for finite differences, which are problems 2 and 3 and part of 4. Yeah, whereas problem 1 is that's all on paper. But so what I want to make sure everyone does is on the assignments page, um, there's a hints file that I put out. And really, you might as well just download that because the questions are in there too. Um, so really everything you need to do for a class is all in that one file, plus some guidance so that I'm not leaving you totally adrift. Although in that file, I don't really talk much about, well, I have some about MATLAB, but I want to give some examples and things like that, because there's a lot of functions that, even if you've taken other classes like 460, 560, where you've dealt with MATLAB, these functions might not have come up. So I want to take some time with those. And I still have a fair amount to cover before the end of the semester, but I'm not too worried about getting all that in. So from now until the end, certainly there'll be time if anyone has homework questions. So so I'm hoping that the info that I give you today can get you started. But how many of you have at least been working on problem 1? Okay. So most of you have been working on it where working is defined loosely. Is that that's better than nothing, I think. Nothing plus epsilon. Okay. All right, and like I said, I'm not really going to focus on that one because I feel like what I'm hoping is that whatever hints that I have put out, like in this document, will at least give you a path through that. But certainly, starting Wednesday, bring your questions. So in other words, the format will be changing a little bit where instead of where I spend an hour and 15 minutes, on average, an hour and 15 minutes just lecturing, that's going to be questions and lecturing. Okay. So I can start with problem 2. A problem of many parts about Poisson's equation on the interval 0 to 1, and then u is 0 on the boundary. Okay. So definitely the ideal starter PDE for a class like this. Okay, and F in this case is given, and I mentioned this before, but I'll just put everything in one place. You integrate to get the exact solution, which you will use to judge the accuracy of your computed solution. Now, the reason why I have integrate in quotes is it's not the function that readily lends itself to integrating like you did in Cal 2. It's a little trickier than that. What I really mean by that, so integrate here is a euphemism for undoing the product rule. Okay, which is also not an easy thing to do. But if you think about what the product rule means, okay, I figured I would not waste any time with my terrible board usage. The derivative of a product, v prime plus gs prime. So suppose you are given this, which you are in this case, and you want to backtrack to that. So in this case, the f that you're given has two terms in it. So can you recognize, for example, what if part of one term is a derivative of part of the other term? Then once you spot that, you've picked out your g. And then from there you can try to figure out what f is by looking at what's left. So that's what I mean by undoing a product rule. Starting with this, looking for something whose derivative is in the other term to figure out what the individual pieces are. Okay. So that's how you get the exact solution for error purposes. Okay. So that's the first thing that you would need to do. The second thing that tells you to do is basically solve this numerically by finite differences. So you're going to write a MATLAB function to do that. So, okay. Now solving a PDE like this in MATLAB, where there's no time dependence, so the time-independent PDE, really what you're doing is you're setting up a system of linear equations, and once you do that, you can just use backslash to solve it. So, in case that you haven't done that in a while, once you have these two entities, your matrix and your right-hand side, then you would just use that to get your solution. So really, the work that's involved is setting up A and F. Okay. Now, how do we set up this system of equations? So first, the matrix. The matrix A is going to be n by n. N is going to be the number of grid points in your solution. Now, the grid points will be j times h. J goes from 1 to n. H will be 1 over n plus 1, because your solution is already known on the boundary. It's 0. So you're only solving for values of u in the interior. So these points, x1, x2, up to xn, you're solving for u at those points. So really what I've done here, unknowns above the line, known values below the line. Okay. So we have n points, but that divides up this interval from 0 to 1 into n plus 1 subintervals. So that's why you have h being 1 over n plus 1. So this is a consequence of the Dirichlet boundary condition to specify u at the two boundary points. So pretty much whenever you're going to have Dirichlet boundary conditions on both sides, that's the spacing you're going to use. You're divided by n plus 1. Okay. Whereas if different boundary conditions would lead to a different spacing. Okay. Now, as far as what the matrix A looks like, this is supposed to approximate minus uxx. So we use the center difference. So minus uxx at a point xj is approximated by minus uj minus 1 plus 2uj minus uj plus 1 all over h squared. J going from 1 to n. So you're going to have n equations and n unknowns. So the n equations come from this being set equal to f. All right. When j equals 1, I'm going to have u0 here. That's not one of our points. Fortunately, we can ignore u0 because its value is 0 anyway. If I give it a different boundary condition, like set u0 equal to something non-zero, you have to move it to the other side. Same thing at j equals n. When j equals n in here, we're going to have u n plus 1. We can ignore that as well. Because the other boundary condition, u of 1, is 0.
Ignore u.
U sub n plus 1. Pretty sure there's no such thing as a clean board in this building anymore. Okay. All right, so the coefficients of these u values tell you what goes in the matrix. So this is for equation j, because of the xj here. So you're going to have 2 over h squared on the diagonal, minus 1 over h squared above, minus 1 over h squared below. So what it'll look like so A is equal to 1 over h squared, 2 is down the diagonal, minus 1 is above, minus 1 is below. So symmetric tridiagonal matrix. Okay. Now, as far as there's more than one way to create this matrix in MATLAB, but for this, it's something I didn't really deal with in class like 460 or 461, but at this higher level, we should deal with it. Use sparse matrices. Okay, so what do I mean by that? Well, okay, just mathematically, forget about MATLAB for a second. Wait, make sure I'm still recording. Yeah, okay. What do I mean by sparse matrix? What makes a matrix sparse? It's going to come up from time to time in 610, but I know that's been plenty long enough to go.
Not including everything?
What? What do you mean?
Doesn't that mean that like it's 1 or 0 or something like as a pattern?
No, that's something else. What did you mean earlier?
Like, kind of spread out, not including every single part of it. I don't know,
Okay. Well, you might be kind of onto it, but
no, I think about it in the sense of some of the research we're doing with derivatives like dense and sparse, but not, I don't know about directly with the
okay.
tagging with matrices.
And the two of you who took 610 last spring, did that flew out of your head?
When I hear sparse, I still think of that.
Oh, your Dartmouth experience?
Yeah.
Oh.
I hate that word.
Oh, sorry. Okay. Billy, none to your tongue?
Is it when most of the entries are 0?
Yes, that's exactly it. Yeah. Gold star for you. All right. So most integers are 0 because it's this tridiagonal. So this matrix has n squared entries in total, but only 3n minus 2 of them are non-zero. Now, in MATLAB, there's two types of matrices, so I'm going to use their terminology and how to refer to them. So, in MATLAB, you have what they call a full matrix. So that's sort of cases where most of the entries are non-zero. So that's just an ordinary 2D array. So you have storage for every single entry. So this is how you normally work by default work with matrices in MATLAB. So if you create a MATLAB if you create a matrix like using a zeros function to pre-allocate it, it will make all the space for a two-dimensional array every entry. And if most of them are still going to be 0, that's a waste of storage. So how is a sparse matrix represented in MATLAB? It's a list of non-zero entries. So in fact, if you have a matrix that was sparse and you printed it out, it wouldn't show up as a nice 2D array like these. It's just going to give you a list that's kind of difficult to read, where you have the ij entry, so indicating which row and column it's in, and then it'll print out aij. So really it's 3 lists: row indices, column indices, the actual entries themselves that are non-zero. So that way it's at least saving storage. Now, there are quite a few functions for working with sparse matrices. I'll only talk about certain ones here. Information on more of them. Okay. So this command, help spar fun. That will give you a list of MATLAB functions that deal with sparse matrices. Okay. Now, those of you, actually, it's for any of you. If you had to create a matrix like this, that's tridiagonal, can anyone think of, what you could always do is use for loops to fill in all these non-zero entries. That'd be extremely cumbersome. Can anyone think of a MATLAB function, forgetting about sparse matrices for a second, because I haven't told you about those functions yet, but what MATLAB function you could use that would make it easier to create a matrix like this?
Triad?
Yes. Okay. So how do you create this? If you're doing it as a full matrix, okay. You could do the following. I could do 1 over h squared. So it's not going to be proper MATLAB syntax, but it'll be enough that you get the idea, close enough, and you get the idea. So the 2's down the diagonal, you can use identity for that. For that part. And then you could use diag to fill in the superdiagonal and subdiagonal. So now what I do if I'm creating this as a full matrix, which I really shouldn't do, but whatever. They're negative.
What is EYE?
That's the MATLAB function that creates the identity matrix of a given size. Yeah, they call it EYE, I guess. I guess they thought it would cause confusion if they used the capital I or something. Yeah, go figure. Okay, so this is identity. So for instance, for the superdiagonal, you could do this, diag 1, where I have to define E beforehand for convenience. It is a column vector. Well, actually, it doesn't have to be. It's a row or column vector. It's a vector of n minus 1 ones. Because if it's an n by n matrix, I have n entries on the diagonal, but I have n minus 1 entries above and n minus 1 below. Each diagonal has fewer entries. Okay. And the 1 here indicates the first superdiagonal. So the diagonal right above the main diagonal. So the second argument indicates which diagonal you want to put these entries on. By default, it's the main diagonal. So that's diagonal number 0. We have positive numbers for going above, and then negative values for going below. So this indicates the first subdiagonal. Okay. So I could say, sorry if it moved here, A equals all of that. So that's how you would create this matrix if you were doing it as a full matrix. Now, if you don't really like sparse matrices, but you need to work them anyway, you prefer to work with full matrices, you could do this. And then, if you have a matrix of either type, you could easily convert from one to the other just by using functions of these names. Because this gives me a full matrix A, and then I can convert. I can say A equals sparse A. does is change how it's represented. So if this comes in as a full matrix, this is the same matrix but represented using the sparse data structure. So then you're not occupying all of that space of those 0 entries. If I wanted to go the other way, I had a sparse matrix. I could say full A to convert to a full matrix. So that's one way you can create A. But it's not really the preferred way. Let me explain the preferred way and then talk about the 2 different approaches. Okay. So creating sparse A directly use a lot of MATLAB functions have for creating matrices have sparse counterparts. Okay, so okay, 1 second here. Forward part. Okay. So there's a function called spdiags. Okay. Now, I don't want to write too much. I don't really want to write actual code for these problems on the board, but give you enough breadcrumbs to work with. So I'm going to explain how spdiags is used. So what do the different arguments mean? So there are 4. Okay, I'll just list these and then I'll explain what they mean. Okay. Now, B is a matrix of the entries that you're putting in the matrix, the diagonals themselves. So one diagonal per column. Okay. So for this case, one column would be the -1s that go below. Another column would be the 2s that go in the main diagonal. A third column would be the -1s that go above. So in this case, you have 3 diagonals to put in, so your matrix B will have 3 columns. Okay. D is a vector of diagonal indices. So it plays the same role as this argument to diag. So you specify which diagonals do the columns of B go on. So for instance, suppose you want the first column of B to go in the main diagonal. The first element of D should be 0. So the same numbering convention. So positive values go above, negative values go below, and 0 is on the main diagonal. So the elements of D should correspond to the columns of B, because you're saying, like, the first, second, third elements of D indicate where the first, second, third columns of B are placed in the matrix. Okay. And then M and N are the size of the matrix you actually want to create. But that means that B has to have enough rows. So for example, the main diagonal is going to have, in our case, capital N elements. So B has to have at least capital N rows. Okay. Now, here's the part about SP diags that's kind of strange. But I guess there wasn't really any better way to do it. Notice here, on the diagonal we have N elements, and then on the super diagonal, subdiagonal, we have N minus 1. That's how many elements we have. So you might think, well, here I want to specify I want N 2's along the diagonal. And if N minus 1 minus 1s, if N minus 1 minus 1's over here. But you can't do that, because B is a matrix. And even though you're specifying the main diagonal, the subdiagonal, the superdiagonal in B, and they have different numbers of elements, you have to specify N elements for every diagonal, which means that on the super and subdiagonal, you can have one entry in each case that's not even going to be used. So, and that's how MATLAB does it. So you're actually putting in B entries that are not going to go in your matrix. Now, in this case, the entries along all these diagonals are going to be the same. So from a super and subdiagonal, you can just give it however many minus 1s you need, and it'll use the ones it wants to use, and it doesn't matter what's discarded. But if the entries along the sub or super diagonal were different, then that would complicate things a bit. So at least for this problem, it's not going to be a big deal. But I just want to make you aware of that difference between the diags for full matrices and SP diags for sparse matrices. You're actually feeding it entries that it won't be using. Okay. So, actually, if you look at the help, okay, so I may not have given away how to create a matrix on the board here, but MATLAB does. So, I mean, I would encourage you to look at the documentation for this function anyway, for more information than I've given here. But yeah, I mean, it's a typical example. Okay. So questions about SP diags. I also want to mention a number of functions. As I mentioned, the EYE function for identity. SPEYE is how you create a sparse identity matrix. So if you're working with sparse matrices, don't use I, use SPY. If you have a need to create the identity matrix. Okay. Now, I've given you two ways to create this matrix as a sparse matrix. Either doing this and then calling sparse to convert, or just doing it this way. Can anyone tell me why this is really not a practical idea?
Computation time?
Well, actually, that would be one thing. What's another?
Does that have to do with N?
Well, I mean, okay, if n is large, it's more problematic, certainly. I mean, if n is small, then it doesn't really matter. But
Just do like the arrow,
no, so it's not an accuracy thing, because the entries that we'll keep are literally the same ones. The final result of this will be exactly the same. But the problem is, if you're doing this first, you're still occupying all that storage of a 2D array. and then you junk it when you do this. And here you're overriding A with a sparse matrix. But if n was particularly large, and you didn't have that much memory, you risk using it up by doing this. And allocating all those zeros that you're just going to toss aside anyway. Whereas here, you don't have that intermediate full matrix. So be wary of, full matrices are still more convenient to work with, just from a point of view of how much code you're typing. So just development time, because you have to figure out how to use all these sparse matrix counterparts and all that. But you're wasting storage and possibly computation time also along the way, because you're having to allocate that space. And MATLAB is taking the time to stick all those zeros in there.
How would you, for the second method, your B's?
Yeah.
That has to do with your n.
So in this case, you have to fill in these columns. But for a matrix like this, B will be a n by 3 matrix. And it'll be a full matrix, but n by 3 as opposed to n by n.
How would you know what it is if you're making the A matrix?
You have to fill this in first. So in this case, for this example, B would have one column that's all 2s, another column that's all -1s, and then a third column that's all -1s.
Okay.
So, and then you will feed this to the SP diag, so it will take those 2s and place it on diagonal number 0.
They have to be in order of. They have to be in a certain order.
The ordering has to. The short answer is no, but the better answer is the ordering in which you place the diagonals in B has to be consistent with the diagonal indices you put in D. So to make sure that they get placed correctly in your matrix. So
It's always going to be n by 3.
for a tridiagonal, yes. So for instance, suppose you put your main diagonal in first in B. Then the first element of this ought to be 0. And you're telling SPDX, take the first column of this and put it on the main diagonal.
So you would say B equals. See, I don't know, because it's a matrix, but it has n rows.
Yes. So you can.
Would it be B equals parentheses? You would do the. No, you can do that.
Well, okay. I'll tell you how to do it because I figure y'all need to know anyway. Okay. So. All right. So creating B or filling in B. Well, first you really should pre-allocate it. So n rows, 3 columns. Now, as an example, I'm saying you have to do it this way. Setting first column equal to 2, let's say. So you could say.
You multiply it by another matrix.
Well, actually, yes, but so I want to refer to the first column, saying on the left side, saying this is where I'm putting this thing, and I think this is what you were talking about. You make a vector of all 1s and you multiply by 2.
Yeah, I was not doing matrix multiplication right in my head, but essentially yes.
And actually this isn't matrix multiplication either. So
okay, I was thinking make like another n by 3 matrix. No, because you can't. I don't know. I'm terrible at matrices in MATLAB. I hate it. I hate it so much. So anyway, continue.
okay. That probably apply to all of you, though, wouldn't it? Okay. All right. Just remember, at least it's still easier in MATLAB than it is in like Python. Yeah. Okay. So you could do that. But since, or this shortcut is allowed, you just do that. The number, because MATLAB will interpret this as saying, oh, you want to put the same value in every single entry. I mean, normally B's have to be the same entity, same size, but with scalars it gives you some leeway. You could have also used a loop, a for loop, to set b I comma 1 equal to 2 for I going from 1 to n. Okay. Now, really, under the hood, all three of these are doing the exact same thing. So here you have an explicit for loop, but MATLAB's doing an implied for loop by doing all this. Okay.
That's just setting that
First column, yeah. Yeah, I bet you can move to the next column to fill the other entries. Notice I'm always talking about putting in -1 or 2. Once you're done, you can divide the whole thing by h squared.
So you would do b colon comma 2 equals -1.
Yes. Yeah, to do the second column. Okay. All right. I was amazed to learn that we're only halfway through class. Well, good, because it's still a long time to cover, I feel like. And then for the vector D, okay, if you were doing it this way, I would say D of 1 is 0. Saying, because all of this has to go on the main diagonal. But the diagonals you're talking about for this tridiagonal matrix would be 0 and then -1 and +1.
+1 being the super diagonal.
Yes, and -1 being the subdiagonal.
Okay.
But if you look at the help page for SP diags, they do it a little differently because they order the diagonals differently. But it doesn't really matter. As long as check your matrix when it's done, make sure that it's that. Okay.
So the vector of diagonal indices, you're just saying that the 2s are a 0, the -1 is +1, and then one on top.
Yes. Yeah, that those columns of B are associated with those elements of D. So that MATLAB knows where to put everything.
There's only one D. There's only one D, right?
Or there's one vector D.
One vector D.
Here I've only set one column of B and one element of D. I would still have to do the same thing with the -1s.
So the 1 is the element or the
This is the first element.
diagonal, like the location of the diagonal? No.
Well, yeah, I'm saying I'm indicating this. Okay,
Like which one is the entry and which one?
these are capital B holds the entries.
Okay.
D indicates which diagonals are placed on. So because I set the first column equal to what I want on the main diagonal, then
The
first element of D has to indicate main diagonal.
Okay, so when you do B parentheses colon comma 2 equals -1, your D would be D2 equals
1 or
One.
-1.
Yeah, 1, and then the third one would be -1. Or vice versa, it doesn't matter. Because
I just don't understand how D is going to be built from that by putting that in the code.
oh, this?
Yeah, like all you're saying is D, because you have to pre-allocate D too.
Oh, it's a good idea. You don't have to. Well, then again, actually, the only reason I had to pre-allocate B was because I'm giving it vectors of a certain size. I could not do this without pre-allocating B, because MATLAB wouldn't know how many rows I want. Yeah, so
So just saying that those 3 Ds it'll build D straight up and you're done.
Yes. Reason why I say it's always a good idea to pre-allocate is that if I did D of 1 is this, D of 2 is this, D of 3 is that, just that, it would still deallocate and reallocate every time I grew D, which is wasteful. But it's not, for a free element vector, it's trivial waste. I tend to pre-allocate everything in sight. But well, I definitely can't fault you for hating matrices in MATLAB, but I guess I'm curious as to what the main frustration is.
I just, when you say, like, all you did was you put B and you said it's the matrix of diagonals, I would have not known how to, that's all you had to do. I don't know, it's just, I feel like every time I have to do a MATLAB question with matrices, I always do it a different way.
Oh, well.
I mean, I don't know, I don't have practice with them, I guess, which I feel like I should, but.
Well, not necessarily. We'll get more next semester, though. Well, yeah, because there's a lot going on with matrices in 461, 561, and you haven't had that. So,
I've seen it in zeros and ones and the
yeah.
colon thing a million times, but I just.
But the thing is, me telling you this is definitely not even close to enough information. Yeah, so I had to do this for any of you to have any inkling what to do.
I mean, I couldn't Google it, but that's what I
Yeah. Well, yes, you can. But the thing is, when I Google things, because I pretty much have no one to ask, so yeah, when I find things, it's like, oh my god, its explanation is awful. Yes, so there's that to bump up against. But once in a while, you find something that's really useful. But yeah, so that's one drawback of getting into a higher level in your career. It's like, okay, no one can help me. Because it doesn't mean you don't need help anymore. You just need help with different things. Okay. But yeah, this is a very different usage than what we have here. So, okay. So, because also, the way you would pre-allocate a sparse matrix, you would not use zeros, because that's for full matrices. You could just say sparse of a certain, and indicate the size, and it'll pre-allocate m by n sparse matrix that literally has no entries in it, because everything is zero. And you could fill in these entries the same way you would for a full matrix. Like you could say, A11 is 2 and A22 is 2. You're allowed to do that. Yeah, it's pretty cumbersome, but yeah. So MATLAB tried to have as much as possible work for both types of matrices, because a lot of functions in MATLAB will accept full or sparse matrices. It needs to work from the same way. So element reference like this can be done with full or sparse. It'll work out the same way. Okay. So, all right, so that's how you create A. But that was only one side of the system equation. You're solving system AU equals F. So I need to talk about F, but that should be a lot simpler. Well, any remaining questions about this? I feel like I spent an eternity on SP diags. Okay. Okay. But yeah, like when I was learning to do the same stuff in Python, I basically wrote 1,000 versions of code that was wrong before finally figuring out the trial and error which one was right. And the explanations were only marginally helpful. So, the right-hand side, f. Now that is just an ordinary vector. No sparse state structures, nothing like that. So the vector f is an n vector, n elements, has to be a column vector for the right-hand side of this ax equals b problem. Now, so the element fj is going to be equal to the function f of xj, where function f is given in the problem. And as I mentioned last time, xj is equal to j times h, where h is 1 over n plus 1. Now, the way I've written this kind of suggests like writing a for loop, which you certainly can do. But a more, I guess, elegant way to do it that's just as efficient. You can create a column vector of x values, and then you can just pass that to, you can just evaluate your function f at that vector. Okay. Because the functions, standard MATLAB functions like sine and cosine, they work on vectors just as well as numbers. And you can pass anything to them and it'll work. But there's one thing I have to point out, because f of x has functions multiplied together. So if you're going to pass a vector into this function, then you're going to have to be multiplying vectors. So if you do it this way, does anyone remember from a prior class, if you want to multiply vectors, you can't use the standard multiplication operator for that. What do you do instead?
Dot.
Yes, use dot star to multiply that. Okay. Now, the x values, you have x1 up to xn. So you have h, 2h, 3h, etc., all the way up to n times h. So you can use a colon operator, 1 colon n, to get a vector of all your indices conveniently. So you don't have to use a for loop for that either. So these are the kind of things that I find myself doing whenever I'm writing code to solve any problem like this. I'm always creating a vector of x values. I'm always using this to get vectors of indices. So carrying out these kind of common tasks for solving PDEs. Okay. Excuse me. Now, for this problem, your f vector will only have this because there won't be any boundary terms because the boundary values are 0. But in general, when you're solving like something like Poisson's equation, you have some boundary conditions, you may have some extra boundary terms to subtract. That'll come up, well, later in this problem, actually. Okay. Okay, so that's the first part of the problem. Solving the PDE. But then, well, actually, in fact, I still haven't got to part A yet, because it tells you to write this program first, before part A. And not only and make sure that it has the accuracy that you'd expect. Okay. So once you have A and F set up, you can solve a system and get your U. So now I need to explain to you, how do you get the error? And how do you check whether it has method has the correct order of accuracy? And actually, I need to tell you about two types of error analysis. What you'll do in MATLAB, and then for part A, what do you do on paper? Okay. Now, the nice thing is for this problem, you have the exact solution. That was the first thing, and it gets worked out. So evaluate the exact solution. Which I'll refer to as U hat, at your vector of x values. So by the time you get to this point, you'll have a formula for the exact solution. So you'll just plug your vector of x's into it. So the idea is now you have your exact solution and your computed solution at the grid points. So then the error is just U hat minus U. So you literally just subtract these two vectors. That's your exact solution at x. This is what you just computed by solving the system of equations. All right. But now we need to be able to check whether this has a right order of accuracy, because this method should be second order accurate. So to verify that there's nothing wrong in your code, that the error is order h squared, what you do is, first, you compute a few different errors. So choose a few different grid sizes, just run your code, because you want to write code that will set up A and set up F and solve a system for whatever value of capital N you choose. Like you can write a function and make capital N a parameter. So go ahead and compute the solution and therefore errors for a few different values of N. What I like to do is use powers of 2 for different grid sizes.
What's this P?
Well, you can pick P.
Oh.
Yeah, it just choose some powers of 2. 64, 128, whatever.
It's the number of grid points, yes.
Yes, yeah. Okay. No need to go to 2 to 22 or anything like that. Yeah, smaller powers of 2 are fine. Okay, then what you do is you want to plot these against the corresponding h's. But don't use plot. Use log. So to plot error versus h. So if you choose a few different n's, you have a few different h's that go with them. So then you can have like a vector of h's, so you need a vector of h's and a vector of and a vector of errors that go with those h's, and that's what you'll plot. Okay. Okay. Now, okay, so for example, you could have a loop that runs a few times. You have a starting value of n, and then you keep doubling it. And then as your loop runs, and with each new value of n and solving a system, you can store each new error, each new h in vectors. And then when the loop is done, then you can plot them. Okay. Now, to check whether this behavior of the error is correct, on the same figure, the same plot, again do a log of h squared. Because the error should be behaving like h squared. So if your code is correct, the error should be like, you should get a line on your graph. And it should be parallel to the line corresponding to h squared. Because when you take the power of h and you do a log-log plot, instead of being like a parabola or polynomial, it's a line in a logarithmic scale. Because if you have y equals h to the p, then you have ln y is equal to p ln of h. So if you're in a log-log scale, we'll plot log y versus log h. P is the slope. So your error needs to have a slope of 2 to be order h squared. But if you plot this also, you can just eyeball it and say, oh, those lines look parallel. To put items in the same plot, the command you use is hold on. So you plot one item, then you do hold on, then you plot the other item. To make sure it goes in the same set of axes. Okay. So that's everything in part 2, problem 2 before part A. This is why I only assigned 7 problems for the entire semester. Okay. They're not all as horrible as this. Okay. Now, let's see, how much time do I have? 27 minutes. I hope not. Okay.
The stuff we were talking about before, I did it in MATLAB, and the first method gave me, but it's because I multiplied it by h. Are you supposed to multiply it by or 1 over h squared?
Yeah, at the end you multiply by that.
So the SP diags, that method just you have to still multiply that by the 1.
Right, yeah, but then you do it a regular way.
Okay.
Okay. Okay, actually part A is it's worked out on paper. Okay. I actually did something like this in class not too long ago, where you take the center difference and you Taylor expand it and simplify things as much as you can. Yeah, it really corresponds to that. So I won't discuss that further, and I do in the hints. So, okay. But really, what you're doing is you're using the center difference. Okay. Well, I'll say very little more than what I did in the hints documents. part A. Oh, really, it should be part B, because what happens prior to part A is quite involved, obviously. So, use the fact that d squared u of x is equal to u of x plus h minus 2u of x plus u of x minus h all over h squared. That is the approximation you're using, the center difference. So these are the items, u of x plus or minus h, that you Taylor expand. Okay. Okay. And that is set equal to f. So when you do your Taylor expansion, eventually appears. And you use the fact that minus u double prime equals f to simplify everything. Okay. Yeah, so all the discussion I had, I think it was last week, about the local truncation error. That's really what's happening here. Okay, so here you're confirming theoretically that the error should be order h squared. Okay. Now, parts B and C have the same goal, and that is to modify this method of solving Poisson's equation to get fourth order accuracy instead of second order, but doing it in very different ways. So part B, you modify the matrix, and part C, you modify the right-hand side vector. Okay. So what happens is you're going to change A to use a fourth order approximation of minus uxx. So what happens is, whereas the center difference requires 3 points, so a diagonal and then one to the left, one to the right, fourth order accuracy will require a total of 5 points. So your diagonal and then 2 to the left and 2 to the right. So that's going to be kind of a pain. You're still going to have something over h squared because it's still second derivative. But what's going to happen is, since you have 5 points altogether, the x's just indicate non-zero entries. What?
The x's indicate
Non-zero entries, yeah. So I'm trying to give you what the structure of a matrix has. Because before, with center difference, it was tridiagonal. This is going to be more like pentadiagonal. So here we have your 5-point approximation. So, and I haven't given you what that is. If you want, you can look it up. I actually don't care how you get it. Well, I do have some information on the hints on how to get those coefficients. But if you want to look it up, that's a good task too. Now, here's the complication. With the center difference, if we were at the boundary, 1 point or the other would go off the edge, and it was okay, because that value of u was 0 anyway, so we can just ignore it. Here too, we have 1 point that's sitting outside, and but the value is 0, so again it's okay. So there's no problem in the second row. What about the first row? We have 2 points outside, but we can't just ignore that. We know the value of u is 0 here. We have no clue about this. So we can't do that. Yeah. So did I just hear a gasp? Okay. All right. Okay. we have to use a different approximation. One that is not centered. In the first and last row, use a non-centered approximation. Okay. Now, I have some code that's been posted on my old 460 or 560 sites that can be used, although, actually, I think on the current version of my site for this semester, they're not posted, because I think it's something I meant to assign as homework. Whoops. But that code is out there, so I could dig it up and send it to you all. Okay. Or again, you can try looking up. So for instance, for a first row, you want an approximation that uses u of x, so u of xj plus h, u of xj plus 2h, u of xj plus 3h, and u of xj plus 4h. So in fact, there would be 5 non-zero entries in the first row for that non-centered approximation. And then the last row would be the same, except to be xj minus h, minus 2h, etc. Okay. So that's how you would update the matrix. The right-hand side will be the same. So then when you solve this system, plot the error like before, like in earlier part, and check the order of accuracy, you should get a line of slope 4 instead of 2. It's supposed to be 4th order accurate. Okay. All right, so once you get to that point, I'm sure there'll be questions. we'll see what happens. Okay. Okay, part C. Instead of changing A, you change the right-hand side F to get 4th order accuracy. You're going to go back to using the previous A, one is tridiagonal. Now, how this would go is in your vector F, before you had that. Just evaluating a function, the given function f, at each interior grid point. But now, you're going to add this on. H squared over 12 times your second derivative matrix. Applied to f, and element j will go here. So you're adding on, so your new f will be your previous f, and you're going to add on this vector. Okay. I should mention, though, that your second approximation, that's the same as minus a, because a is meant to approximate minus uxx. Okay. Now, there's one complication with using your second derivative matrix with f, because f does not satisfy the boundary conditions. So those values like u of x0, u of xn plus 1, they can't be ignored. So really what you're going to have is, okay, so what goes in here is really going to be minus af. So that takes care of everything except the boundary points. So now you have to add something onto that, but only for the first and last elements. So nothing else is going to change. So you're going to add on 1 over h squared f of x naught, or really it's f of 0. And then nothing in between. And the last element, you're going to add on 1 over h squared f of 1.
It's a vector.
Yes. Or since you're only changing the first and last elements, you can make this vector, and then you can say like element 1 is itself plus this, and then element n is itself plus. All right. So I don't really care how you do it. Okay. The reason why it's 1 over h squared times f of 0, f of 1 can be seen here. Suppose that, for example, suppose x is a first interior point. Then x minus h sits in the boundary. That's x equals 0. So notice this is over h squared. So that's why we have that here. And then same for the other boundary point, where the u of x plus h is a boundary value. Okay. Now, what's going on here is in part A, when you do a Taylor expansion and you find out what the error is, depending on like what you put on the left side or the right side, this is the error term you get. It's supposed to be h squared over 12 times actually the fourth derivative of f is what would show up in your Taylor expansion. But uxxxx, well, uxx is equal to minus f. So your Taylor expansion in part A will give you this, but because you use the exact solution, we know it's also equal to this. So the purpose of adding this term is really to cancel the error term you get from Taylor expansion. Because your error term is order h squared. If you have a way to cancel that, your next term is order h to the fourth. So this is a nice little trick that extends from your theoretical error analysis to cancel out your leading error. And that actually, so that one little change with the same A improves the order of accuracy a lot. Okay. Okay, not much time left. So I'll talk about this last part of problem 1, or problem 2. The only problem I've talked about today. And then we'll see what happens. So part D, the only thing that's being done in this problem is you're changing the underlying PDE. You're changing the F. And this time it's a function of a discontinuity. So it's equal to 1 for x up to a half, and then 0 after that. Okay. So it's just asking how the error behave. So your code for generating A and the right-hand side of your system, that doesn't change at all. You're still going to do the exact same thing. The only thing you have to do different here is you need to recompute the exact solution to compare against. So what that involves is u of x is going to be minus the integral, so really it's a double definite integral it's really just saying just integrate f twice and then negate. So that way, minus u double prime will bring you back to f. But what happens when we integrate this that makes the solution not entirely unique? Because this is an indefinite integral. What do you have to remember to add on when you take the integral? Plus c. And I haven't said anything about how you choose a plus c. So, and you're going to get two of them. You're going to get two constants of integration because you're integrating twice. So you choose your two plus c's. Okay. This is weird. Because you need to meet these conditions. U and U prime are continuous at 1/2. So you have to make sure that, so for instance, you integrate this and you get x plus a constant. Oh, okay, yeah. At first I was thinking, I got too many conditions here, but you're actually not going to have 2 plus c's, you're going to have 4 of them. 2 from here, 2 from here. Because you have to do each piece separately. So you're going to have 4 plus c's. So to make a solution unique, I have to impose 4 conditions. So here are 2 of them right here. U and U prime must match up at this interface point when you switch pieces. And then the other 2 conditions are just boundary conditions. So now you have 4 unknowns, 4 equations. So basically solving a system of linear equations to work that out. Well, what you can do is, when you integrate once, and you have 2 c's introduced, you can make sure the results continuous at 1/2. So that will at least eliminate one of the unknowns, and then you keep going from there. Okay. Once you have that, then you're going to solve this PDE numerically, just like you did in the previous parts, and you're going to plot the error like before. No change to that code. And see, do you still get the same order of accuracy? Because this is your error term. And it depends on the second derivative of f, which is also the fourth derivative of a solution. But here, the second derivative of f, even f itself is not continuous. So it doesn't even have a second derivative at 1/2. So what you're going to find out is, does this affect the accuracy of the method in this case? So you'll find out. Okay. So, yeah, there's only 2 minutes left anyway. Thank goodness. So, all right. Let's just see what happens on Wednesday and how far you get. But still have a fair amount of semester left.